Okay, time for another video. Now I was thinking if these were like really professional videos done, by BYU Studios, there would be like some theme song soundtrack while you looked at this slide here and it would fade out as we go to the next slide. So let's try that out. We all live in a yellow submarine. Okay, let's talk about the difference between lateral and angular magnification. What we have talked about previously in this class is when we said magnification before, what we really meant was lateral magnification, meaning if I have some object here, and I have a lens here, and then I make some image over here, or whatever, right? I'm comparing the lateral size, the size of this thing in the direction, perpendicular to my optical axis, and comparing that to the size of this perpendicular to the optical axis, right? We never really talked about how this dimension changes, right? And we're not going to. You can figure that out on your own if you'd like to. But the point is, what we've talked about before is what we call lateral magnification. It's just magnification with a capital M is lateral magnification. It's the height of the image divided by the height of the object. But lateral magnification is not always indicative of what you care about. For example, if I look at the moon through a telescope, I don't care how much bigger the image of the moon is. I care how much better I can see the moon. If I have a telescope that makes an image of the moon which is twice as big as the moon itself, but it's 4 times as far away than the moon itself, I don't see the moon any better. I see it worse. I see less detail. So what we usually care about when we're looking with our eye through a device is how much bigger angles become. Alright, so I look at the moon, and this crater, from the bottom to the top of this crater is, say, 1, milliradian, for example. Alright? It would be nice if it was 100 milliradians, right? And so when we talk about angular magnification with a little m, we're not comparing the height of the image to the height of the object literally or laterally. We're comparing the angular size of my image to the angular size of my object, right? So by angular size, I mean put my eye right here, right, and I look at some object over here. There's my object. I look at this and I say, what angle does that object subtend? Alright, that's the angular size of an object. Now if I move my eye closer, the angular size gets bigger, right? So one way to increase your angular size is just get closer to an object, right? But for example, we're going to talk about microscopes and magnifying glasses. The idea with those is, yeah, I could just put this ant closer and closer to my eye and see more and more detail, right? Because the angular size gets bigger and bigger. But that doesn't work because my eye cannot focus on things that are extremely close. Alright, so I need an instrument to magnify the angle of the object. Alright, so make sure you understand the difference between lateral magnification and angular magnification. And when we talk about optical instruments like telescopes, microscopes, and magnifying glasses, it's the angular magnification that we care about. Another thing to be aware of is with lateral magnification, the height of the image is just the height of the image, right? We always know what that is. We compare that to the height of the object. It's pretty straightforward. But when we calculate the angular magnification for a device, we have to think about kind of what's the best we can do with and without the device. There's kind of some loaded dice that we play with. So pay attention. We're not going to just like throw something in front of our eye and keep everything the same. We're going to compare best cases with and without the device. Alright, so let's first talk about a magnifying glass. So with a magnifying glass, what we do is we have our eyeball here. We put a lens up, and we're going to assume that our eye is right up to the lens, alright? And then we look at some object, but it makes some image, and is that image, does it have a larger angular size or not? Alright? Okay. Well, it turns out what we're going to compare, I'm not going to compare how big does this thing look with the lens and then take the lens away and compare it to that. I'm going to compare what's the best I can see it with the lens versus what's the best I can see it without the lens. So without the lens, right, we're not going to leave this object out here wherever I put it to look at it with the lens. I mean, I can move the object around. Actually, when I use my lens, it's Actually, my object is going to be closer than my image, but that's a moot point. The point is, when I look at an object through the lens, I'm going to move that object to the point which gives me the best view of that object. When I take the lens away, I'm not going to leave the object there. I'm going to move the object to where I get the best view of it with my eye. So when we look through with our lens, the angular size of the image we see, we're not going to compare that to how the angular size of the object without the lens. We're going to compare that to the angular size of the object when I put it where I can see it the best. And where can I see it the best? At my near point. So we're going to assume a healthy eye, and what we'll be doing when we calculate the angular magnification of a magnifying glass is we're going to compare how well we can see it with the lens to how well we can see it when it's 25 centimeters away. All right, what's the angular size 25 centimeters away versus the angular size looking through the lens? Now it turns out that the best view we get with a magnifying glass is when we adjust things so that the image is at our near point. But it turns out sometimes it's not such a big difference between the magnification, angular magnification when we put it at our near point and when we put it at infinity, and it's more comfortable to look at things at infinity. So sometimes when we calculate the magnification for a magnifying glass, we'll calculate the magnification for the case when the image is at infinity. We'll look at both of those here in just a minute. In your homework, I'm only going to ask about images at infinity, which is kind of funny because I recently looked, and I'll show you some data later, which says that people usually, when they specify the magnification of magnifying glass, they use the image at your near point at 25 centimeters. All right? Of course, nice thing about image at infinity is if you have a different near point than someone else, you get the same magnification. All right, so here we go. How does a magnifying glass work? So I said what we're going to do is we're going to have our eyeball right here. All right? I'm going to put a lens right here. And I'm going to have an object. All right? And actually, no, I'm going to have an object right here. Let's have an object right here. All right? And light from that object comes to my eye. Light going through the very center doesn't bend, right? So I know this ray of light is going to be like this. So my image is going to be somewhere along this line. I know that. All right? If I draw my rays, I know the ray that goes right through the center of the lens doesn't bend. So it looks like that light is coming from somewhere over here. So I use all my other rays to figure out where that image forms. But I know wherever it forms, it'll be along the tip of my arrow will be along this line somewhere. So the angular size of my image is just that angular size right there. But that's the same angular size as the object, right? So obviously there is no magnification for my magnifying glass. Well, we know that's not true, right? Because we're not comparing the angular size of my image to what I would see if I just took the lens away, right? We're comparing to what I would see if I put the object 25 centimeters from my eye. So the idea with a magnifying glass is the angular size of the image is the same as the angular size of the object, but the lens allows you to put the object closer to your eye to make its angular size bigger. Because with this lens, you can see things much closer to your eye than you could without the lens. All right? So let's consider the first case. All right? So the angular size of my object, call it theta naught, all right? The angular size of my object is just, in the small angle, that's going to be the arctangent of the height of my object and the distance. It's going to be the arctangent of the height of my object divided by the distance, which is 25 centimeters, right? So when I look at it with my naked eye, I'm going to put it 25 centimeters away, and its height is h, and its angular size is arctangent of h over 25. We're going to assume small angle approximations. We're looking at tiny things with our magnifying glass, so let's just call this h over 25 centimeters, because the arctangent of an angle in radians, right, is really close to just the thing, right? This is a small, if you go and you plot arctangent of x as a function of x, you'll find that for small x it's just equal to x. All right, so this is a small angle approximation that I've made. And now we need to look and say, well, what is the angular size of our image? I'll call it theta prime. All right, well, where am I going to put my image? There's two options. The first option is I could adjust the object such that my image is at my near point. So this would be my maximum angular size I can get, is when I adjust the object such as the image is at my near point. All right, well, let's look at this. Well, in order to find that, I need to either know the size of the object and how far away it is from me when I'm looking at it through the lens, or I need to know the height of the image and then divide by my near point. All right? Okay, so I'm going to put my image at my near point. How do I find the magnification? If I know the magnification, I know it's at my near point, I can figure out the angular size. Or if I know what P is, then I can find what it is. All right, so to find the magnification, I know Q is going to be, for the maximum angular size, Q is going to be minus my near point, 25 centimeters. If I know P, I can get the magnification, or I can just directly calculate the angular size. How do I find P? Well, 1 over F is 1 over P plus 1 over Q, so P is equal to 1 over F minus 1 over Q to the minus 1, right? And so then I can say, oh, well, my angular magnification, I can write that as, in the small angle approximation, H divided by P. So that's H divided by P, and P is, oh, it's H times 1 over P, and here's 1 over P, right? So it's going to be H times 1 over F minus 1 over Q. All right, so that's equal to H divided by F minus H divided by Q. There we go. All right. Another way I can find the size is I could have taken H prime divided by Q, right? The height of the image divided by the image distance. All right? But H prime is just H times the magnification, which is minus Q over P, and this is all divided by Q. Boom, boom, that's gone, all right? And I'm just left with H minus H divided by P. There you go. Except I made a mistake because this distance is not Q, this distance is minus Q. There, good. Okay, so this turns out to be exactly the same thing we found before. All right, so the angular size is just H divided by P, and we find P using this equation right here, right? We've done this before. And then what I really care about now is I want to find the angular magnification. So the magnification is the angular size of my image divided by the angular size of my object. The angular size of my object right here is H times 1 over F minus 1 over Q, right? That's that right there. And then the angular size of my object, when I look at it with my naked eye without the lens, and I put it 25 centimeters away from my eye, that's just H divided by 25 centimeters. But that's equal to, look, the H's cancel out, and I'm left with 25 centimeters over the focal length minus 25 centimeters over Q, but Q is negative 25 centimeters, right? And so this is just equal to 25 centimeters divided by F plus 1. All right, so that's the magnification, but that's assuming that I put my image at my near point. All right, now this is kind of lots of stuff, so let's review what we did. We calculated how big would the object appear if I look at it with my naked eye, and we said with my naked eye the object has a height h, and I'm going to put it at my near point, which is for a healthy eye 25 centimeters. All right, and then we took a small angle approximation and said, oh, that's just h over 25 centimeters. That's the angular size when I look at it with my naked eye. Then to calculate the angular size when I look at the image through my magnifying glass, to compare to that, well, I said, well, to get the best view of this, I'm going to put the image at my near point. So Q is going to be negative 25 centimeters. Then I said, well, if I know the height of my image and Q, I can get the angular size of my image. But I pointed out that the angular size of the object, but placed really close to your eye because we're using this lens, is going to be the same, right? We have similar triangles. So we said, if I can find P, then the angular size will just be, in the small angle approximation, h divided by P, or equivalently, it's the height of the image divided by negative Q. All right? So we found what P was, and we plugged it in, and we said the angular size here is just h over P, plug that in and we get this, and of course Q here is negative 25 centimeters. All right? We looked at the image, we figured it that way, and we said, oh, it's just h prime divided by minus q, but h prime is just h times the magnification, which is minus q over p. We got the same thing, h over p, and we already found that h over p is equal to this. So then we divided the angular size of the image with the angular size of the object viewed without the lens, and everything came out to be this. So the magnification is just 25 centimeters over the focal length plus 1. So smaller focal length means bigger angular magnification. Well, we said another thing we could do is instead of putting the image at our near point, we could put it at infinity. All right, it gives us less magnification, but it's more comfortable for our eye. All right, so if we put the image at infinity, then 1 over f is equal to 1 over p plus 1 over q, but q is going to be minus infinity, and then we say, oh, p is just going to equal f, right? So we're going to put the object at the focal length, which means that the angular size in the small angle approximation is just the height divided by the distance, which is f. And then we say, oh, the magnification then is going to be theta of the image divided by the angular size when we view with the unaided eye. And this is just h over f, and this theta naught, if we can go back up, waiting for PowerPoint. PowerPoint. So, while we wait for PowerPoint, let me tell you a story. I'm just kidding. This is really lame. I'm going to have to start all over again. Huh. Sheesh. Microsoft. Ah! Here we're back. Alright, so the angular size of our object was just h over 25 centimeters. The h's cancel out, and we just get 25 centimeters over f. So there is the angular magnification if we put the image at infinity. So if we kind of in the range that we can use our magnifying glass, we can hold the magnifying glass to our eye and adjust where the object is, where we place the object. We will be able to focus on it over a range of places we can put it. If we put it in the right place such that it forms an image at our near point, the magnification is 25 centimeters over f plus 1, but if we move it such that the image is at infinity, the magnification is just a little smaller. It's 25 centimeters over f without the plus 1. So that's how a magnifying glass works. That's the basic idea right there. Okay, now I found some specs on reading glasses, all right, and for example, I found one that claimed to be a magnification of 1.5, and it said that the lenses had a power of 2.25 diopters, which means their focal length is 44.4 centimeters, all right? And it turns out that this magnification is just equal to 25 centimeters over 44.4 centimeters plus 1.9375. So this is probably a rounding. They're probably rounding this to a nice even number, right? So what they intended to do is use the 25 centimeters over f plus 1 way of defining magnification. So when they say the magnification is 1.5, they're assuming you're adjusting the object such that the image forms at your near point. All right, they also had one they claimed had a magnification of 1.75, and they said those lenses had a power of 3 diopters, which means their focal length is 33.3 centimeters, and that comes out to be pretty much exactly 25 centimeters over f plus 1. So magnification of 2, power of 4 diopters, that means the focal length is 25 centimeters. Everything works out. So when you look up these up on the table, if you know the power in diopters, the focal length, or the magnification, they all tell you the same thing. All right, they're connected. Okay, let's talk about a microscope. How does a microscope work? Magnifying glasses are great. And in fact, the very first microscopes were basically just magnifying glasses with a really short focal length lens. All right? But you can do better with what we call a compound microscope. And the idea with a compound microscope is you use 2 lenses. So what you do is you have your little amoeba here that you're going to look at. All right? And so you put a lens here. This lens is known as the objective. It's called the objective because it's near the object. All right? Now, in a microscope, what this objective is going to do, instead of making a virtual image for you to look at, it's actually going to make a real image. All right? And so you make some real image some distance away. So here's your object right here, like this, and you come over here, all right, go through your focus, whatever. and you're going to make this image over here. Now, how big can you make the angular magnification when you make real images? It turns out you can make the lateral magnification arbitrarily big by putting your object arbitrarily close to the focal point, right? 1 over f is equal to 1 over p plus 1 over q. If you make p really close to 1 over f, or sorry, p really close to f, then this thing is almost equal. This has to be really small, and q can be really big. So you can make q ginormous, and then the lateral magnification is negative q over p, so you can make a gigantic image, all right? How big is the angular magnification when you're making a real image? Well, you're going to compare what you can see without this lens to what you can see with it. Without the lens, you put this amoeba 25 centimeters from your eye. With the lens, you put your eye 25 centimeters away from the image. So you're looking at the object or the image at the same distance, right? So it turns out for a single lens making a real image, the angular magnification happens to be equal to the lateral magnification, and the lateral magnification can be made arbitrarily big. So now, why don't we use magnifying glasses this way? Why don't I make a real image with my magnifying glass and then I can make things arbitrarily big? Well, there's two reasons. The main one is the real image forms a long ways away from the lens. So you're going to have to hold this lens way far away, right? And if you want a really big magnification, maybe your arm is not long enough. Another reason is that's a real pain, right? Even if you're going to hold this magnifying glass out the length of your arm and get the magnification you can get from that, your arm's going to wiggle, all right? You're far away from the lens, so you don't have a very big field of view, all right? So there's problems with that. That's why we don't do that with a magnifying glass. But in a microscope, we're looking at something typically that's very small, so we don't really care if we have a big field of view, all right? We don't need to look 180 degrees. We just want to look into this very small area and see this little amoeba. All right? And then the other problem of holding things very steady, we overcome that by mounting everything into a tube, right? A microscope is a big, heavy device, very rigid device, all right? So the idea with a microscope is I mount this lens in a tube and I hold my sample on, in the same system so that things don't move relative to one another. And then I can just come and I can look at this image here and get really high magnification. But we're not done, all right? In a compound microscope, we do this, and then we say to ourselves, I can get even more magnification if instead of just looking at this image, what if I looked at this image through a magnifying glass? Hey, then this image acts as the object for my magnifying glass, which makes another image that allows me to get my eye closer to this image and see more detail. So in a compound microscope, the magnification that I get is first the lateral magnification of the objective times the angular magnification of my eyepiece acting as a microscope, as a magnifying glass. All right? But the lateral right, because the angular magnification of my objective, because it's making a real image, is the same as the lateral magnification. So that's going to be the angular magnification of my objective is the same as the lateral magnification of my objective, and the lateral magnification of my objective is minus q for the objective divided by p for the objective, all right? And then the angular magnification of my eyepiece, it's just a magnifying glass, and that's got a magnification of 25 centimeters over f. And then do we put a +1 here? Am I going to put the image at my near point or at infinity? It turns out with microscopes, the magnification is typically so big that that +1 just doesn't make any difference. So why bother with it? So we're going to just use the infinity expression, even though we may not put it at infinity, because that +1 is going to be small compared to all this other stuff. All right? We usually use a very small focal length for my eyepiece. But we're not done. What is Q for the objective and what is P for the objective? Well, the idea is I'm going to try and make this image really big with my microscope. All right? So I want Q to be much bigger than P. If Q is much bigger than P, all right, that means that P has to be about equal to the focal length, right? Because if Q is really, really big, then 1 over Q is really small. That means that 1 over P is really close to 1 over F. So we can kind of substitute in here. Instead of putting P naught in here, I'm just going to put the focal length of the objective, all right? Then we've got my 25 centimeters after the eyepiece and so forth. Okay, what is Q? What is Q for my objective? Well, the point is I'm going to have a really short focal length magnifying glass here. That's what my eyepiece is. So that means I'm going to put this image very close to that, right? So roughly speaking, Q is the length of my whole microscope, all right? There's a little space right here, there's a little space right here, but those are going to be small compared to this length. So roughly speaking, this distance right here is the entire length of my microscope. So we like to then, in this approximation, we'll say, look, the magnification of my microscope, it's pretty much just 25 centimeters times the length of my microscope divided by focal length of the objective times the focal length of the eyepiece. And there is the angular magnification of your microscope. All right? So you can make your microscope better by having shorter focal length lenses, and they work really hard on that. If you've ever looked at a real microscope, the objective lens, it's actually a compound lens. It's a whole bunch of lenses together, stuck together to cancel out aberrations so that you can get a good lens with a really short focal length. Similar thing with the eyepiece, all right? So they try and make these focal lengths really, really short. And then they try and make the microscope long, if they can, the tube, right? And sometimes the tube will even have mirrors that folds the image so the light goes back and forth to effectively make it longer so that you can get more magnification. Now, it turns out, though, you can't just win this game forever, because right now we're assuming that light travels like rays. It doesn't travel like rays. And in a little while, we're going to find out that there are limits to how well you can focus light based on the fact that it's a wave, and waves tend to spread out. So eventually, you try and make your microscope better and better by making it longer and longer, making your focal length shorter and shorter, and eventually you're done. You just can't you can make the image bigger, but you can't make it sharper. So you can make the angular size bigger, but it's also blurrier. And that's maybe because your optics aren't perfect, or maybe your optics are really good, you're just limited by the wave nature of light. And we'll talk about that again later. But for now, this is what you need to know, magnification of a microscope. All right, our final topic today is the telescope. The telescope. All right, how does a telescope work? Okay, so imagine, if you will, we're looking out at Mars, and there's some object on Mars that's so big, but we can't see it. It's a huge thing on Mars, but we're so far away, it's just really hard to see. Okay, so imagine, if you will, I've got light coming from this object on Mars, all right? Here are two light rays coming from, right? So here's my object right here. I didn't draw the arrow. Whoops, let's go back. You need to see this, all right? So here's my object. We're going to take light. Let's just look at two special rays that come from this point and see where they come into focus. All right, so here we go. Here comes the crater on Mars, and it's that far from this other crater on Mars, and we want to see how that angular size changes by looking through the telescope. All right, one of these rays is a special ray because it's parallel to the optical axis. The other ray is special because it goes through the focal point of the first lens of our telescope. All right, and with those two rays, I can figure out what's going to happen. All right, so let's look in my telescope. First of all, this is the angular size when we look at this object with our bare eye. Now, unlike a magnifying glass, we're not going to compare what we see with the telescope to what we see when we put the object 25 centimeters from our eye, because that's not fair, because you cannot put this object on Mars 25 centimeters from your eye. So we're going to compare the best we can see without the telescope to what we can see with the telescope to find our angular magnification. So theta naught is the angular size as seen putting my eye here in front of the telescope. Now, whether I put my eye here or put it back here and remove the telescope doesn't make much difference, because the length of my telescope is small compared to the distance to Mars. So anyway, that's the angular size of my object right there. But what happens to these rays when they hit my telescope? All right? Oh, yeah. That's the angular size there as well. If we look at this triangle or this triangle, they're both the same theta naught. Okay, so there's the focal point of my first lens. All right, my lens has another focal point over here. This is the objective. This is the eyepiece. All right. Now, in a standard telescope, okay, we're made of two converging lenses. What I do is I put their focal point so that this lens right here has a focal point here and here. I adjust them so that the two focal points between them are right on top of each other. All right. Now watch what happens when I do that. This ray that is going parallel, it's going to bend and go through the focus, right? This ray that's going through the focus, it's going to come out parallel. There we go. And so it looks like I form an image right here really close to the focal point. of this lens, all right? What happens to the light when it goes through this lens? Well, this ray right here, I can use the same rays because this one's traveling through the focal point of this lens as well. It's going to come out parallel. This one's parallel. It's going to bend and go through that focal point, all right? And it looks like I see an image over here, all right? So here's my image. My object is way over there, and there's the angular size of my image. Well, notice something. The image is smaller than the object. So the lateral magnification of my telescope it's got a magnitude which is less than 1. But although my image is smaller than the object, it's much, much, much closer. So it's easier to see detail. The angular magnification is going to have a magnitude greater than 1. All right, so let's see if I can figure out what that angular size is. Let's zoom in here. All right, so I'm comparing this angle to this angle. All right, and you can see they're two triangles, but they share a common side. All right, so this angle right here, if I call this distance right here, let's call it S. All right, theta naught is going to be equal to the arctangent of S divided by the focal length of the objective, right? Which in the small angle approximation is just F over the focal length of the objective, all right? The angular size of the image is just going to be the arctangent of S divided by this distance right here, which is the focal length of the eyepiece, or in the small angle approximation, just S over the focal length of the eyepiece, all right? So the angular magnification is going to be theta image divided by theta unaided eye. Well, okay, I guess to be fair, the way we've defined theta is kind of the opposite direction. So maybe I should put a minus sign here, right? Because here the object is up, whereas here the object is inverted. So then this becomes negative S over the focal length of the eyepiece divided by S over the focal length of the objective. The S is canceled out, which is good because they're sort of arbitrary. And we get focal length of the objective over the focal length of the eyepiece with a minus sign to tell us the image is inverted. So there's the magnification of a telescope. So the game with a telescope, long objective, short eyepiece. All right? What limits? I mean, it seems like we ought to be able to make a lens with a really long focal length, right? A piece of plate glass has got a focal length that's infinitely long, right? But it turns out it's impractical, first of all, to make telescopes which are too long. All right? Another problem is, we're going to talk about it again later, because light is a wave, things actually get blurred out. And typically when people build high-end telescopes, they're more worried about the diffraction, the wave issues, than they are about the angular magnification. So angular magnification, you can make it whatever you want it to be, but then you better make sure that your telescope actually doesn't just make things big and blurry. All right? But there's the angular magnification for a telescope made with two converging lenses. Now it turns out if you replace the eyepiece with a diverging lens, you can make an arrangement where you get this magnification without the minus sign. All right, so that's another possibility. Your book doesn't really talk about it though, so we're just going to skip over it. But if you are going to build a telescope for yourself someday, it's kind of nice to not have the image inverted, so you might look into that. Most really nice telescopes though don't actually use lenses. Well, at least for the first one, they'll use a mirror because it's easier to make good quality mirrors. Mirrors don't have spherical aberration. It's easier to support a mirror in your telescope. So it's the same physics though, only they'll use a mirror. All right? And then the eyepiece, typically if you were to buy a telescope, I believe typically the eyepieces are converging lenses, so you get things inverted, but there's a little device you can stick before your eyepiece which flips things over for you if you don't like that. All right? Okay. So imagine I have a telescope with an objective focal length of 1 meter and an eyepiece focal length of 4 millimeters. First of all, how long will my telescope be? Well, remember, I have my two lenses and I align them such that they have a focal point right between them. So this distance will be 1 meter and this distance will be 4 millimeters. So from the center of this lens to the center of this lens, it looks like it's going to be 1.004 meters long. right? Just add those two focal lengths. What's the angular magnification? Well, the magnification is, these are both positive focal lengths, right? So it's going to be negative the focal length of the objective, which is 1 meter, divided by 4 times 10 to the minus 3 meters, all right, which means 0.25, negative 0.25 times 10 to the 3, all right, and the meters cancel out, it has no units, or negative 2.5 times 10 to the 2, okay, negative 250. All right, is it a good telescope? That's a lot of magnification. I had to be able to see lots of cool stuff, right? My daughter once bought a telescope that had like 80 times magnification for like 12 bucks. Yeah. So what we saw, you look at the moon and you see a big blurry moon that's, 80 times bigger, but you can't see any detail that you can't see with your naked eye, all right? So magnification isn't the full story. If you buy a telescope, make sure it's a good one, because if the optics are not good, things will get blurry. But even if your optics are really, really good, we have to worry about the wave nature of light. And so you may go to a reputable telescope builder and say, why don't they make one with 100,000 times magnification? Well, because it doesn't make sense for a telescope that size, because the wave nature of light does not allow you to make sharp images that are that big. So there's more than just magnification to a telescope. And we're done!